Hello, and welcome back to the web series Developing SPECTER using Innoslate's digital thread. My name is Mallory Jones, and I'm a systems engineer here at Spec Innovations. In the previous videos, I introduced and initiated the Lunar Rover project, demonstrated Task 1, 2, and 3, and overviewed the Innoslate integrations used to perform testing. In this ninth video of the web series, I will demonstrate the work conducted to perform environmental and performance analysis as deliverables requested from the Break the Ice challenge. Again, these were not submitted to the challenge since we entered late, but rather they were used as a guideline for determining the lunar rover's prototype performance parameters. Phase 1 of NASA's Break the Ice challenge required contestants interested in the competition to conduct an environmental analysis of their proposed lunar rover system. The purpose of this environmental analysis was to ensure the SPECTER rover prototype can withstand the extreme environmental conditions on the surface of the Moon. These environmental conditions include low temperatures at the delivery site ranging 50 to 200 degrees Kelvin, low temperatures at the excavation site ranging 40 to 100 degrees Kelvin, reduced gravity of 1.62 meters per second squared, lunar dust with electrically charged particles smaller than 20 microns, and a vacuum atmospheric pressure of 2.28 times 10 to the negative 12. Each environmental condition previously listed is mitigated in some way. A warm electronics box was utilized to enclose the lunar rover's avionics to keep equipment at operable temperatures in the cold environment. A wide-set body frame and rugged wheels stabilized the rover while navigating unpredictable terrain. Non-pneumatic tires are also used to stabilize the rover in the lunar gravity. And lastly, tire fenders protect the rover body from dust abrasion or damage to the equipment. Phase 1 of NASA's Break the Ice challenge also required contestants interested in the competition to conduct a performance analysis of their proposed lunar rover system. The purpose of this performance analysis was to validate SPECTER's functionality and efficiency. The parameters calculated and evaluated for SPECTER included landed mass of the rover's equipment, mass of the NASA water extraction plant, total landed mass of total water delivered during the mission lifetime, power consumed by the rover, power consumed by the NASA water extraction plant, and total power consumed during the mission lifetime. As part of the performance analysis, a mass analysis was conducted to determine the mass to be landed on the surface of the Moon for excavation of the lunar rover's mission. To determine the mass of the full-size rover in proportion to the LEO rover prototype, a ratio of rover carrying capacity to rover mass was used. The LEO rover has a carrying capacity of 5 kilograms and a mass of 5.4 kilograms, resulting in a ratio of 1 to 1.4. The average carrying capacity of a full-size rover is 100 kilograms. Using the 1 to 1.4 ratio, it was estimated the full-size rover body mass would be about 108 kilograms. Therefore, the prototype rover to full-size rover has a mass ratio of 1 to 20. In addition to the lunar rover body, other equipment and components were landed on the lunar surface to support the mission. This reduces the rover's available carrying capacity and increased the total mass landed on the Moon. Each additional component was weighed and scaled to full size using the prototype to full size ratio of 1 to 20. A total additional equipment mass of 53.12 kilograms was calculated to be added to the rover body. The carrying capacity remaining for the full-size rover after the additional components was calculated to be 46.8 kilograms. Adding together the water extraction plant mass of 700 kilograms, the tire fender's mass of 16 kilograms, the mass of the full-size rover and additional equipment, the total landed mass was calculated to be 877.12 kilograms. Consequently, since the carrying capacity is reduced, the amount of regolith or water that can be stored at any time is also reduced. This will require more excavation and delivery cycles to be executed in order to reach the mission goal of collecting 10,000 kilograms of water. In the next part of the performance analysis, a water analysis was conducted to determine how much water can be collected and delivered in 365 days or how fast the goal of 10,000 kilograms of water can be reached. To begin this water analysis, it was first determined what type of regolith will be mined throughout the mission based off water concentration levels. The water extraction plant's mass flow rate of 100 kilograms per hour provided by the Break the Ice Challenge was used to calculate how much regolith would need to be excavated in order to extract 10,000 kilograms of water. 20 to 100 centimeters deep in the lunar rock, the regolith has a granular, icy consistency with 4% water concentration. If this type of regolith was excavated throughout the rover's mission, then it would require 250,000 kilograms of regolith to be excavated in order to extract 10,000 kilograms of water. 100 to 350 centimeters deep in the lunar rock, the regolith has a hard, icy consistency with 10% water concentration. If this type of regolith was excavated throughout the rover's mission, then it would require 100 kilograms of regolith to be excavated in order to extract 10,000 kilograms of water. After comparing the two regolith's water concentration levels, the 4% concentration was selected to be excavated during the mission. It was selected in order to limit stress on the excavator claw and the robotic arm. Continuing the performance analysis, a power usage analysis was conducted to determine how much power will be consumed during the lunar rover's mission. SPECTER prototype field test results determining the rover's power consumption were used to calculate the total amount of power the lunar rover will use during its excavation mission on the moon. These results, including the battery capacities, current draws, and power conversion rates, were all inputted in the mission scenario action diagram created and demonstrated in Task 1 Research Web Series video. Once the mission scenario action diagram was updated and the model simulated, the battery life, power consumption, regolith excavation, and water collection were tracked throughout the rover's mission lifetime using resource entities. However, before execution, the goal of collecting 10,000 kilograms of water had to be scaled down to match SPECTER's prototype performance parameters. To do so, a prototype to full-size storage unit ratio 1:5 was used to provide the mission scenario action diagram a goal of collecting 10,000 kilograms of water. Innoslate simulators calculated an estimated 4,800.556 ampere hours of energy to be consumed during the lunar rover mission to collect 10,000 kilograms of water. The last component of the performance analysis included conducting an excavation analysis to verify the lunar rover will be able to excavate 250,000 kilograms of the selected 4% concentration regolith. SPECTER excavation functionality field test results were also inputted in the mission scenario diagram calculating the total amount of regolith the lunar rover will excavate. The performance parameters updated in the action diagram included the excavator claw, maximum load capacity, average excavation rate, and maximum storage capacity scaled from prototype to full-size rover. Once all the performance parameters were inputted in the mission scenario action diagram, Innoslate simulators were executed to verify the full-size rover will excavate 250,000 kilograms of 4% water concentration regolith and extract 10,000 kilograms of water. The simulation results also confirmed that 5,000 excavation cycles are needed during the mission lifetime. This is well within the excavation claw's maintenance limitation of 1 million cycles. To summarize the results of the performance analysis and the expected performance capabilities of SPEC Innovation's proposed lunar rover system, the full-size rover has an estimated carrying capacity of 46.88 kilograms and an estimated mass of 161.12 kilograms. Combined with the water extraction plant's mass of 700 kilograms, the total landed mass is estimated to be 877.12 kilograms. The total amount of energy to be consumed during the mission is estimated at 4,800.556 ampere hours. The total amount of excavated regolith has an estimated mass of 250,000 kilograms. And lastly, the time to collect 10,000 kilograms of water is anticipated to be 10.67 months. These results meet the mission's goal of collecting 10,000 kilograms of water within 1 Earth year. Up next in the web series, Developing SPECTER Using Innoslate's Digital Thread, is a final video closing the lunar rover project and what's to come. Thank you again for being here today, and I'll see you in the next video.